Hey, welcome back to your favorite pre-calculus class. We're going to take a look at systems of linear equations, specifically substitution and elimination. Here's our objectives for this lesson here. We're going to start out talking about systems of equations. So a system of equation is where you have two or more equations given, and here's some examples here. In this first one we have two equations, 1, 2, as well as two variables. You notice we have x's and we also have y's, right? Here we've also got two more equations, right? 1 and 2, and we've got x's and we got y's. We've got two variables again. Now here we got three equations, and so three equations and three unknowns, x, y's, and z's throughout, right? Here's two equations, and it looks like we got not only x's and y's, but we've also got z's. So we got two equations, three variables. Finally, here we've got four equations, but we just have x's and y's, and it looks like we've also got z's. So three variables there. So those are some examples of systems of equations. Now the solution to a system of linear equations, if they're linear, okay, so if we got lines, it could be either consistent or inconsistent. Consistent means we have a solution. So if we have two lines that cross, like this one here, we have an answer, so it's consistent, and it's independent. There's only one solution, and it's whatever that xy value is. And that xy point is the only xy value that satisfies both lines, both linear equations, okay? That's where they intersect. Now, if there's no intersection, that means they are parallel lines, so they have the same slope but different y-intercepts. Then we're inconsistent, right? There's no point that satisfies both equations because they're parallel; they never touch. And the third situation is where we have coincident lines. In other words, we have the lines are right on top of each other. So here's the first line, and then the second line is right on top of that thing. It is the exact same equation. There it is in red. So you have an infinite amount of xy values. There's an xy value that satisfies both. Here's another one, xy, that satisfies both. Anyways, there's infinitely many points because they cross at an infinite amount of points, right? Because they're the exact same line. So that's called consistent and dependent. In other words, the solution depends on the xy. There's a bunch of xy's that could satisfy both equations because they're the same equation. All right, I kind of overkilled that. Anyways, graph the let's graph a system of linear equations to find a solution. So we have 3x minus y equals 5. First of all, let's put this in slope-intercept form. So let's solve equation 1 for y. And let's graph this thing. So we got negative x is negative 3x plus 5. Multiply everything by negative 1. So we got 3x, or divide by negative 1, however you want to think about that. We got y equals 3x minus 5. So here's our y-intercept. Let's put the point on there, negative 5. And then our slope is up 3 over 1. There's our slope. Up 3, positive 3, right 1, positive 1. So up 3, 1, 2, 3, and over 1. Put a point, if it lets me. Put a point. And then up 3, 1, 2, 3, and over 1. Put another point. Come on, let me put a point. Oh my gosh. There we go. Anyway, it's not. This is kind of driving me nuts, but there we go. Sorry about that struggle there. Let me do next one. X plus 2y equals negative 3. Let's solve for y. So it looks like we're at negative 1.5 right here. And then we're down 1 and right 2. Down 1, right 2. So it looks like these two intersect at that point 1, negative 2, right there. So it looks like 1, negative 2. That appears to be the solution here for this consistent and independent solution. And let's check it. if 1, negative 2 is a solution, then when I plug it in to each one, I'll get a true statement. Let's check. So I got to plug it into both of these, and it's got to be true. In other words, that point, 1, negative 2, has to lie on both lines, linear equations there. There's the first one. Let me plug it in here. Sure enough, both are true. So 1, negative 2 it is. There's a little better picture of that. Alright, so how about solving it? So that's graphing it. That's solving it by graphing. Now let's solve it by substitution. So what we're going to do here is I'm going to let's take this first equation. Well, first of all, I'm going to think, what's the easiest variable to solve for? And it looks like this y is by itself. In other words, its coefficient is 1. If you have a coefficient of 1 or negative 1, I'd probably go with that one and solve for that variable. So let's solve for a variable. So I pick any equation and solve for a variable. So 3x plus y equals negative 9. Let's solve that. And then I substitute into the other equation. So the other one we have negative 2x plus 3y equals 17. And this y, right, y is equal to negative 3x plus 9, is going to go in right there. It's going to go in for y. So I have negative 2x plus 3 times, and I'm going to plug that negative 3x minus 9 in. And I'm going to solve. So negative 2x minus 9x minus 27 equals 17. Combine like terms. Add that 27, both sides. So we have negative 11x equals 44. Divide by negative 11. Looks like we got negative 4. So our x value here, now we know that x is negative 4, right? And so all we got to do is plug that in to either of the other equations. So let me just pick the first one, 3x plus y equals negative 9, and let's plug that x in. We got negative 12 plus y equals negative 9. I'm going to add 12 both sides. Looks like y is 3. So we've got negative 4 comma 3 as our solution. And of course, if we were to check that solution, we just plug it in, right? Plug in negative 4, 3 into both of those equations. And you can see negative 9 equals negative 9, 17 equals 17. And there is your solution to that consistent independent situation there. All right, how about solving by elimination? So we've done graphing, we've done substitution. How do we solve by elimination? Elimination means we're trying to get rid of one of the variables. And so what I'm going to do is I'm going to get rid of, I'm looking at this 5x, and now think about this for a minute. If I was to add these up right now, would a variable eliminate? And I'd say, well, no, it's not, because I'd add up 5x plus 1x, 6x, 2y minus 1y is a plus y equals 1. That's not what I want to happen. I want one of these variables to cancel. Okay, so what I'm going to do is, let me think about this for a minute. I'm going to look at this and I'm going to say, all right, which of these variables is easiest to eliminate? And maybe it's deuces, but I'm going to pick the y's. If this is 2y, I need this to be negative 2y. Well, it's already a negative 1y. So all I need to do is multiply equation 2 by 2. So if I multiply both sides of this equation by 2, so So if I take this side by 2, which means I got to do the other side by 2, then what I'm going to have, top one stays the same, 5x plus 2y equals negative 5. So when I multiply both sides of this bottom equation by 2, look what we have, 2x minus 2y equals 12. And then when I add those up, I get 7x here, and 2y minus 2y, that's gone. That's what I was trying to do. I was trying to eliminate those. And then negative 5 plus 12. So now I can solve for my variable. I've eliminated a variable. So x equals 1. Okay? So now we know they both have an x value of 1. They both have an x value of 1, okay? And so now that so that's step 1 is get rid of one of the variables. So multiply one of the equations by a constant so that they eliminate. So that's step 1. And then step 2, now that you know that variable, you can just plug it into either equation. I'll just pick the bottom one, x minus y equals 6. I know my x is 1. Negative y equals 5, so y equals negative 5. So my solution, x comma y, is 1, negative 5. And you could plug those back into both equations, right? Substitute them back in to make sure that they satisfy both equations, and you'll be good to go on that. Okay, there's that walkthrough as well. And then you can check it, right? All right, how about a little word problem here? Well, can we make a linear equation of this? A movie theater sells tickets for $8. Seniors receiving a discount of $1, so the seniors are $7 each. One evening, the theater sold 521 tickets and had a revenue of $4,000. How many of each type of ticket was sold? So let's let X be the tickets sold at $8. Y is the senior tickets sold for $7. Okay, so X is number of tickets sold at 8. Y is the number of tickets sold at $7, right? Now they sold 521 tickets, so we know X plus Y, there's 521 tickets sold. Now let's do how much money they made. 8 times the number of tickets sold at that amount, and then they're $7 each, and Y is the number of tickets sold at that amount. To make, they had $4,000 that night. All right, so there's our two equations. 8x plus 7y equals 4,000. And then x plus y equals 521. And let's go ahead. So if we are going to do this by elimination, what we're going to do is let's get rid of the y's here. So if I have one of these is 7y, that one needs to be negative 7y. So I'm going to multiply both sides of this times negative 7. And let's see what we get. And I'm going to bring that down here. So I got negative 7x minus 7y, and then 521 times 7, and we got 3647. So that's from equation 1. The equation 2 here, 8x plus 7y equals 4,000, stays the same. Now we're using elimination. This is what we wanted, negative 7y plus 7y. We want those to eliminate. And we got negative 7x plus 8x is a 1x from there. And then 3647, whoops, that was negative. I'm sorry. That's a negative right there. Okay, negative times each of those, right? So what is that? 353? 353. So there's 353 tickets sold at $8. That's the number sold at $8 each. And remember, x plus y, there's 521 tickets sold. So if we already know there's 353 sold for $8, then 521 minus 353, and we got 168 that are sold at the discount price. Okay, that's an example of elimination. All right, so what happens if you're solving this what will happen if you get an inconsistent system of linear equations? Let's go ahead and do this. Let's do this by substitution. I see that that's real easy to solve for. Let me take equation 1 and solve for y. So 7x plus y equals 4. Subtract 7x, negative 7x plus 4. Now I'm going to substitute that into the other equation. So 14x plus 2y equals 1. Here's what y is, negative 7x plus 4. That's going to go in right there. So I got 14x plus 2 times negative 7x plus 4 equals 1. So I got 14x minus 14x plus 8 equals 1. Ooh, those are gone. Then the question is, does 8 equal 1? Surely it does not. This system is false. In other words, there's no solution. There's no solution here. Oops, no, I can't even spell that. No solution. In other words, this is inconsistent. This is inconsistent. And think about this for a minute. 7x plus y equals 4. That's y equals negative 7x plus 4, right? So it's like right here, down 7, right 1, looks something like this, right? Now the other equation, if I was to solve that for y, subtract 14x, negative 14x plus 1, divide by 2, look at this. It's got an intercept of 1/2, and it's down 7, right 1. This thing is parallel. So they never cross. That's why there's no solution there, all right? These got the same slope. So inconsistent. So that's how you recognize that algebraically, is you're going to have something that false comes up, okay, whether you're doing it by substitution or elimination. All right, so let's go ahead and do this one here. Now we got 4x minus y equals 6, and I'm gonna let me think about this. Let me eliminate the x's. Okay, so notice this is negative 12x. I want this to be positive 12x, opposite sign but the same number, right? So positive 12. So what I'm going to do is since it's already positive 4x, I'm going to multiply this by 3, both the right side and the left side. So equation 1 becomes, once I multiply that all through, both sides of the equation, 12x minus 3y equals, and then multiply the other side by 3, 18. Bottom equation stays the same, negative 12x plus 3y equals negative 18. And then those cancel. That's what we wanted. We got 0. But then notice this. Ooh, look at that. Negative 3y plus 3y. I got 0 here. And over here I got 18 minus 18. I got 0 here. So what's going on is, well, this is always true. Yeah, that's true. 0 equals 0. And what this means is this is infinitely many solutions. Because if you were to solve this, notice if you were to solve both of these for y, negative y equals negative 4x minus 6, so y equals 4x plus 6. Now take the other one, negative 12x plus 3y equals negative 18. Solve that for y. X minus 6. And so you've got, whoops, this was a minus 6. Sorry about that. So you got y equals 4x minus 6. You got y equals 4x minus 6. Oh, these are the exact same line. They're right on top of each other. That means any of these xy values are a solution. So there's infinitely many solutions to this. Okay. And so what you say, or how you express that, is you say, another way of expressing infinitely many solutions in set notation, you just say it's a set of all xy values such that y equals 4x minus 6, where x is any real number. Okay? Or if you want, you could also say, well, it's a set of all xy, and then you could do it in terms of x. And so you just solve solve for x, and you get x equals 4th y plus 3 halves, or y is any real number. So any of those is another way to express that. Just take one of the variables, solve for it. Okay, I'm going to stop right there. We're going to go into 3 equations in just a second. That's a good time to stop. Thank you.